So in a way, section 16.3 is a continuation of the previous section doing line integrals. Independent of path means that if you're supposed to integrate and curve C looks something like this, or whatever curve C looks like, and you're supposed to integrate this vector valued function over the curve C. Well, if f is independent of path, that means that you could take any path you want. As long as you get from point A to point B, any path will give you the same answer. And of course, just having a straight line would be much easier than having some parametric curve like this. So how do you know when capital F is independent of path? Well, it's also called conservative. So capital F is conservative, or in other words, independent of path, if capital F happens to be the gradient of some other function. So for example, number one, how about if f is equal to the natural log of x plus 2xy and x squared. So if this is equal to the gradient of some function, that means whatever the function f was, lowercase f, somebody took the derivative with respect to x and they got this. And they took the derivative with respect to y and they got this. So let's say they took the derivative with respect to x and they got the natural log of x plus 2xy. Well, if this is the derivative, then integrate to find out what the original function was. Oops, I wasn't supposed to write that, just f. So integrate. If you integrate the natural log of x, that's going to be x natural log of x minus x. And if you integrate 2x, that's going to be x squared, and y is a constant. Then there could be some other function, which we could call c, which was either literally a constant, or perhaps it had y's in it, and so when you took the derivative of it, it became a 0 right here. Okay. Then go on to this one. So somebody took the derivative with respect to y and they got the answer x squared. So then integrate this one with respect to y, and it means that it would have x squared times y plus some other constant. So I could call this one c1 and this one c2. And now compare the two. So this is a green, so it definitely has to have this. And then this is a constant. When you're taking the derivative with respect to y, anything that has an x is a constant. So this right here is actually that part right here. So then f is equal to x ln x minus x plus x squared times y. And then that's it. So yes, f is conservative because capital F is equal to the gradient of what we just got. Now, how do you actually integrate? So if you're supposed to integrate from point A to point B, and perhaps at first it said follow this path right here, and you're like, wow, that's going to take a lot of work. So instead you can, so if capital F is conservative, and specifically capital F is the gradient of lowercase f, then when you integrate over curve C, so this being curve C, of f dr, well then that means integrate, so just replace the f with the gradient of f dr, and then this is saying integrate the derivative. Well, if you integrate a derivative, those two cancel each other out, and you'll just get the lowercase f function, and then evaluate that from point A to point B. Or in other words, it's going to be f of b minus f of a. Then for example number 2, so let's say that capital F is this vector valued function. It has 2x e to the 2y plus 4y cubed. That's for the first component. For the second component, it has 2x squared times e to the 2y plus 12xy squared. And then part A, show that capital F is conservative. Or in other words, f is equal to the gradient of some function. So if you have the lowercase f, then this is the derivative with respect to x, and this would be the derivative with respect to y. So let f sub x, or the derivative with respect to x, be the 2x e to the 2y plus 4y cubed. And now integrate that with respect to x. So if you integrate this, that's going to be x squared, and this is just considered a constant. So it'll be x squared times e to the 2y. And if you integrate this with respect to x, this is all a constant, so it's going to be the constant times x. And then there could be some other plus c constant. Now move on to this one. So the derivative with respect to y is the 2x squared e to the 2y plus 12xy squared. And then find the antiderivative with respect to y. So f, lowercase f, will equal, so this is what we're integrating, and the integral of e to the 2y is e to the 2y, and then divided by 2 because of the chain rule. Well, when you divide by 2, it's actually going to cancel that 2. And then for this one, it's going to be y cubed over 3, and then that 3 will divide into this, leaving a 4, x and y cubed, and then perhaps plus a constant. So let's see, if you compare them, they actually agree. X squared e to the 2y, so definitely include those two. And these two are actually the same, so we don't even need a plus C1 or plus C2. So therefore, I'm done with part A. F is equal to x squared e to the 2y plus 4x y cubed, and the gradient of f will equal the capital F. Okay, then on to part B. Example number 2, on to part B. Evaluate the line integral of f dr if C is a curve and the endpoints are 1, 5 and 8 comma 9. So you could have some fancy curve that goes between these 2 points, or you could just go straight from one to the other. So the integral of f dr over c is equal to, and so then we could just skip to the part where we found out what f is. And if you look back even one more page, we could skip straight to this part. So basically, by finding this, we actually did the integrating. So when we did this step right here, we actually did the integrating, so we don't have to integrate again. So it's just going to be the lowercase f, so that's going to be x squared e to the 2y plus 4x y cubed. And then evaluate that from 1 comma 5 to 8 comma 9. So then start at the top, so substitute x is an 8 and y is a 9. And plus 4, x is an 8, y is a 9. All right, then go to this point. So minus, when you substitute that x is a 1 and y is a 5. X is a 1, y is a 5. So for that, I think I should use a calculator. So it's going to be 64, and then e is to the 18, plus that would be 32 times 9 is cubed. And then minus, this would be e to the 10. And then distribute the negative, so minus 4 times 5, which is cubed. Oh goodness, that is a lot. 420,223,8826. That's a lot of money. Okay. Suppose you have some capital function f. F is equal to, and then let's say that it's in 2 dimensions. And then this is the vector valued function. Is f conservative? So back to the question that we started with on this section, is it conservative? So you could do it the long way and say this is the derivative with respect to x, this is the derivative with respect to y, and then integrate this one with respect to x, integrate this one with respect to y, etc. Or there's a faster way to check. So the answer is yes, if you take m and take the derivative with respect to y, you take n and you take the derivative with respect to x. So if m is actually equal to this red one right here, and you then take the derivative with respect to y, you're actually finding the second derivative with respect to x first and then y. And for this one, if you take the n and you take its derivative with respect to x, you're finding the second derivative with respect to y first and then with respect to x. And if those two second derivatives are equal, yes, it's conservative. Now the only bad part is this is a quick way to find out if it's conservative, but it does not actually tell you what the little function f is, the lowercase f. You guys still have to find that out yourself. But as example number 3, is the integral of x squared y plus y e to the x dx plus xy squared plus y e to the x dy independent of path. So in other words, this is the m and this is the n. So m is equal to the x squared y plus y e to the x. And then find the derivative of that with respect to y. So that would just be x squared. And the derivative with respect to y would just leave e to the x. Then, this is the n, so capital N equals xy squared plus y e to the x. And now take the derivative of that with respect to x. So the derivative with respect to x will be y squared plus y e to the x, because we're taking the derivative of e to the x with respect to x. And then is this one equal to this one? And the answer is no. So that means that it is not independent of path. So that means if we would have set f of x equal to this and f of y equal to this, and then we integrate each one with respect to its variable, and then we try to match up the parts and put it all together, we would have just been wasting our time. So that's a fast way to find out, is it even independent of path? Okay, then one more that is independent of path. So for example, number 4. So capital F is equal to y squared times z plus 2x z squared 2xyz, and for the third component, xy squared plus 2x squared z. Well, now we have 3 variables. So if this one is independent of path, then for the little f, or the lowercase f, somebody took the derivative with respect to x and got this. They took the derivative with respect to y and got this. And they took the derivative with respect to z and got this. So let's see. If the derivative with respect to x is y squared z plus 2x z squared, then integrate with respect to x. So then lowercase f would be, this is just a constant, so it would be x times y squared z, and the antiderivative of 2x will be x squared, and z squared is constant, and then there could be something else. And that something else could have y's and z's, or perhaps numbers. Then move on to the middle part. So somebody took the derivative with respect to y, and they got 2xyz. So then integrate with respect to y, and this will become y squared over 2, and that over 2 will cancel this 2. So then it's going to be x y squared z. Deja vu, that's the same thing. And then it could have its own constant, and this constant could have x's and z's in it. Dun, dun, dun. All right, move on to the third part. So somebody took the derivative with respect to z, and they got xy squared plus 2x squared z. And then take the antiderivative with respect to z, so this is going to be z times xy squared. And then the antiderivative for this will be z squared over 2, which will cancel that. And then it could have its own constant, which could have x's and y's in it. So let's see. Now when you compare them, this has x, y squared, z, x, y squared, z, x, y squared, z. So they all agree there. Therefore, f is going to have x, y squared, z. And this says, hey, by the way, you also need x squared times z squared. And this one agrees you need x squared times z squared. And this constant is saying that you could have something that has x's and z's in it. Well, that something is going to be x squared, z squared. And then we have all of the parts, so that one is conservative. Now, actually use that. So continuing with example number 4, evaluate the integral over the curve C for capital F dr if C is given by this. X is equal to the square root of t, y is equal to t plus 1, and z is equal to t squared. So this makes some type of curve as it goes through space. And by the way, this is for t between 0 and 1. So rather than having to substitute all of these in here and then find out what this curve looks like, etc., all you need to know is the beginning point and the end point. So if t equals 0, what's the beginning point? That'll be 0, that'll be 1, that'll be 0. So that's 0, 1, 0. And what about the end point when t equals 1? So that'll be 1, 2, 1. So that means that if you integrate f dr over that curve, then you could just use this function because we basically already did the integrating on that previous page. And then all you need to do is plug in these numbers, 0, 1, 0, and 1, 2, 1. So starting at the top, put in 1, 2, 1. And they're in order, so it's going to go 1, 2 squared, 1, plus x is a 1, and z is a 1. And then minus, use these numbers, which means that's going to be 0 times 1 times 0. And then that's going to be 0 squared, 0 squared. So this is just 0. This is going to be 2 plus 1 equals 3.